Alright, so here we're going to talk about three different scales. We're going to talk about section 4.3 concepts, talking about logarithmic scales, number one, in general, and number two, specifically, three different scales that we took a look at. Number one, pH, number two, decibel scale, number three, Richter scale for earthquakes. So in general, on a logarithmic scale, the number is represented by its log, by its logarithm. So on a logarithmic scale, base 10, the number 1000 is represented by its log. Log base 10 of 1000 is what? 10 to what power is 1000? Has to be 3. The number 1/100th is represented by its log. Log base 10 of 1/100th is, let's see, 10 to the yth power equals 1/100th. We gotta get that 10 base down here, so that would be y equals -2, because 10 to the -2 power equals 1 over 10 squared equals 1 over 100. That's what we're looking for. So our y is -2 because 10 to the -2 power is 1 over 100. Sounds good. So that's our number, -2. 1/100th is represented on a log scale by -2. So if we're taking a look at a linear scale, the linear scale would be kind of looking like this. We'd start somewhere at 0 and we'd go up to, let's say, 1000. And that number here, this 1000, in our real number linear scale would look at 1000, or would be at 1000. Our number 1/100th in our linear scale would be really small. It'd be right down here, and it'd be really kind of hard to tell it from 0. So there's our 1/100th on our linear scale. And it'd be hard to kind of compare anything much bigger than this, let's say 2000 or 3000 or 10,000 even, because then your scale gets so much bigger. If we take a look at a log scale, we can compare things a little bit easier. And we could say that on our log scale, here's our log scale. On our log scale, this 1000 is represented by, here's my 0. 1, 2, 3, there's my 3. Not necessarily in line here, it just kind of happens that it's lined up here. So there's my 3 here. Over here, and that's where this 1000 would be represented here. That would be one of the spots here. This 1/100th would be represented back here at -2. And now we can see that 1/100th, kind of a small number, especially compared to that 1000, it kind of fits pretty well on a log scale. So we can see that every time we, so I guess we can compare 1/100th to 1000 and say it's 1, 2, 3, 4, 5, 10 to the 5th power larger than that 1/100th. So if we go on a log scale from -2 up to 3, we've gone 5 steps in the log scale, and that means that in a linear scale, that would be a difference of 10 to the 5th factor, a factor of 10 to the 5th. This one is times 10 to the 5th bigger. This 1000 is 10 to the 5th times as big as 1/100th. So there's kind of the difference and the way that, I guess the reason that we have log scales to compare very, very small numbers and very, very large numbers, kind of on a scale it's maybe easier to work with. So specifically then, if we're talking about pH, here's a pH scale. pH scale talks about this. pH equals -log of log base 10 of a hydrogen ion concentration. In a solution, there are some hydrogen ions, and the concentration of those hydrogen ions tells us how acidic or how basic that is. So here's our pH scale, and this, in general, here's our pH scale. On a pH scale, the higher the hydrogen ion concentration, the lower the pH. Because in general, here's a log scale. Log scale would look something like this, going through 1, 0. A negative log scale would look like this. This would be y equals -log of x. This is y equals log of x. So here's our log scale. Here's our negative log scale. If we take a look at any x value here, we'd have a positive number over here. If we take a look at that same x value we should have, in general, a log scale would be this much up here, but we're taking the negative of it, so that means that this goes down here. And this is a negative log scale. That's a positive log scale. So that's why if the hydrogen ion concentration goes up, the pH goes down. So let's take a look at specifically what this means. If I give you pH equals -log of log base 10 of, and I give you a hydrogen ion concentration of, oh, let's say 5 times 10 to the negative 5 power. I'm just going to throw out a number and say, what's that log? If we take a look at that log, we'd take first of all the log base 10 of 5 times 10 to the negative 5 power, and we get negative 4.301 dot dot dot, and that would be our log. But we'd have that negative log down here. pH of this hydrogen ion concentration would be the negative log of this. Log of that is negative 4.301. Take the negative of a negative because that negative is still there. pH becomes 4.301 dot dot dot, or about 4.3. Now a different situation might be is if I give you let's say a pH, and we have to find the hydrogen ion concentration. We start with the same idea. There's our definition of a pH. pH equals negative log of a hydrogen ion concentration. If I give you that the pH is like 6.8, we measured it, let's find out what the hydrogen ion concentration is. We can do the same idea, and all we're doing is rewriting this and reminding ourselves that this is a log base 10. And we have to use the idea that if I give you log base b of x equals y, well, that's the same thing as b to the yth power equals x. And keep in mind, it goes both ways. If we've got an exponential statement, we can make that a log statement as well. So there's our log base b of x equals y is the same as b to the yth equals x. So we can take this logarithmic equation and write it into a exponential equation. The only problem is this negative sign is in the way, so we have to multiply by negative 1. Negative 1 times 6.8, negative 6.8 equals negative times a negative is positive, so we got a positive now, log base 10 of my hydrogen ion concentration. And now I can say, now I can use the idea over here to translate from a log statement into an exponential statement, saying that 10 to the negative 6.8 equals my hydrogen ion concentration. So all we have to do is now take 10 to the negative 6.8, and that's our number. So if we evaluate 10 to the negative 6.8, that's equal to 0.000000158, which is equal to 1.58 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, negative 7. Either one of these is correct. Neither one is more correct than the other, but probably it's just standard to kind of write it in this form, 1.58 times 10 to the negative 7 power. And that would be our that would be the hydrogen ion concentration if our pH was 6.8.